Hi everyone, are you able to hear me and see my screen clearly? All right, great. So let's start. Let me just check the audio. Okay, great, great. All right. Hi Abhinav, hi Balaji, hi Bintao, hi Kamal, hi Noor. Great to have all of you in the session. Today we are going to continue the discussion from the logistic regression. So, till last time we had talked about the various linear models and we'll see how we can apply the linear models in the uh, in classification. So logistic regression is nothing but the regression used for classification. All right, here we go. So so logistic regression is basically a binary classifier. It is used for estimating the probability that an instance belongs to a particular class. Okay. For example, what is the probability that this email is an spam? Okay. So essentially, even though we have gone through the classification already, let me give you some more context. So to classify an email into spam and not spam is a standard classification problem. Okay. So so basically what we do is we compute the probabilities. Okay, so we estimate the probabilities. If the estimated probability is greater than 50% of an email being spam, then the instance belongs to that class, as in the email is spam. And the positive class we denote it by 1, and as in if whatever is our classifier, the positive label is 1. And otherwise, but it is 0. The negative label, as in when it's not in spam, then it's 0. So, so basically, if we talked about two things. One is we represent things with probabilities. Second, we further go ahead and compute the probability. If greater than 50%, then put it 1. Okay. Now let's go ahead. So just like a linear model, a logistic regression model computes the weighted sum of the input features plus a bias term. Unlike regression model, a logistic model outputs 0 or 1, the logistic of the result. Let me take a step back and explain. So what did we do in linear regression models? What did we do in linear regression models is we computed the weights, we multiplied with the various. Okay, just give me a second. I'm being logged out. All right. So somebody probably from my team is logging in. That's why I'm logging out. Okay. Just give me a second. And all right. Okay. All right. So what did we do in linear regression is we, first of all, we had something called weights, and we multiplied the weights with the actual values of x, and then whatever was the value, we considered that the prediction, correct? In the case of logistic, the value of y's on the right hand side are 0 or 1s. Okay, so all we do is we compute the value as we did in linear regression. Just we convert that value into 0 or 1. We compute that value, whatever we did, like in the usual linear regression, we convert that decimal number into zeros and ones. Okay, that's how we make the normal linear regression or normal regression into the. So we convert the normal regression models, linear regression, into logistic regression by converting first of all the value into probabilities from say 50% between 0 and 1, and then converting that decimal number between 0 to 1 into either 0 or 1. Okay, that's what we are going to see. How are we going to convert that? So all we do is here I think this will remind you. Remember the hypothesis function? Okay, hypothesis function here is basically there is one more function outside the basic one. This part I think you will remember that there were thetas and we multiply each of these thetas, as in there are m number of linear equations, and all of those m m set of thetas are being multiplied to x, and whatever is the result used to be our hypothesis function. But here the hypothesis function is after passing the result of this via something called a logistic regression. So we do things still here exactly the way we did earlier, just that we put one more thing called logistic. Okay, what it does is it converts these values into the values between 0 and 1. Okay, it converts whatever value it is, it converts it into 0 and 1. That's what is the logistic function. So the hypothesis function, instead of returning an arbitrary value, it returns a value between 0 and 1. Okay, a decimal number lesser than 1, greater than 0, or equal to 0, or equal to 1. So here, okay, now, what kind of sigma? This is called a sigmoid or logistic function. We also call it sigma. So what kind of sigmoid uh, would convert any number in between 0 to 1? So one of the examples of sigmoid function is this. One of the examples of sigmoid function is this. It is 1 by 1 plus e to the power minus t. Okay. Now let's take a look. Let's take a closer look at sigmoid. Please pay attention to this one because this will keep coming again and again. All right. Uh, Pratik, I think you again logged into my account. Could you log into your own account? All right. I was just logged out. Sorry about that. All right. So now let's pay attention to it. This will come into use at many places, even in deep learning and other places. This will come into use. So what is so special about this function? This function that you see here, this function is nothing but 1 by 1 plus e to the power minus t. Okay. So what does it do actually? So what it does it do is it converts anything into something between 0 and 1. Okay, so this is how the graph looks like. This is how the graph looks like. Okay, so if the t is really small here, negative, so the value is going to be 0. It is going to be almost 0. And if the t is very big, the value is going to be 1. And the value here is is between 0 and 1. Now the question that arises is that there are so many other functions that can convert any value in between 0 and 1, right? There could be standardization. We talked about two kinds of standardization and so on. So there are many functions that could convert any arbitrary value into something in between 0 and 1. Now, why are we using sigmoid? So is everybody clear? So here, let me put it again here. Let's take a look at it. If this number, if t becomes really big, so that means e to the power minus t, correct? That means this number is going to become really small, right? Because it's minus t, minus negative, and this t is, let's say, really big number. So if you put a power of something negative and really big, so what this number becomes very small. When this number becomes very small, this will become 1 by 1, right? That means 1. Okay. So if t is really big, then the outcome is going to be 1. If t is really small, this term is going to be huge. This term is going to be huge, and hence it's going to be the denominator is going to be really huge, and therefore the overall value is going to be almost like 0, correct? Because if denominator is really huge, the overall value goes really down, right? So that's what is happening here. And and so essentially, when t is really small, the value of this sigmoid function is 0. And if t is really big, the value of this sigmoid function is going to be positive, as in +1. Okay, here. All right. So this is 0. So basically, sigmoid function is capable of converting any number in between 0 to 1. Now, question is, what other functions did we have? What other techniques did we have that could convert any value into something between 0 and 1? One was standardization technique, right? We find min and max, and then we divide each value by delta of min and max, and so on, right? So that also, we would convert any number into something between 0 and 1, but that one required computation of min and max, correct? And hence, if that one min and max, the function required to go through the entire data set. But in case of sigmoid, that's not really required. It can convert just any arbitrary value into something between 0 and 1, right? Is this making sense to you? Exp is the e to the power. You see this e to the power? E is nothing but 2.3, so it's that number. All right. So it could have been even 10 to the power something. Then also the behavior of this sigmoid function would remain the same. Okay. So we can take any number instead of e. So yes, theoretically, the sigmoid function can be defined as 1 by 1 plus exponent of t. And here e is generally 2.3. But if you want to experiment, you can also put 10 here. Okay, that's also right. So theoretically, yes, that's right. Just that the ability to compute this sigmoid function is very common in most of the libraries, and hence people generally stick to this. Now, the other question that arises is that why sigmoid function is important? The first answer was that for computing here, for converting any number into something between 0 and 1, we did not require the other numbers like min and max. The other very important part is that this this sigmoid function would be is very decisive. Okay, let me ask you this way. Okay, if I ask you that please interview somebody, and you have to answer either yes or no. All right. So so you have to be like sigmoid. You have to be like sigmoid, that that you would have to either clearly say yes or no, right? And that's what is required in case of classification also, that we don't want to be always on the borders, right? Had it been, say, okay, so please feel free to ask questions, because I know that there are many doubts in this, and here it's a little difficult to, you know, uh, understand it in one shot. Okay, so let me just explain. So imagine that there was, instead of sigmoid, okay, how should I draw it? Let me just draw it like this. Okay, and let's just draw it like this. Okay, so our sigmoid is something like, let's say this is our 0, this is our 0, and sigmoid is something like this is really bad. That's the reason I failed in arts. Okay, so something like this. All right, so I could just, yeah, okay, this is, I think, better. All right, so if you see, the sigmoid has gone from here and suddenly went up. So the confusion area is only this. Okay, only for some values of t, only for some values of t, there is a slight confusion, right? Meaning, so if the value of t is this, it'll clearly say no, right? So again, what are we trying to do? We are trying to, using sigmoid function, we will be taking a call whether a particular instance is negative or positive, right? So the case that we were taking, say, email spam, for example, right? So let's say our regression looks like this. Number of times each word's frequency has occurred. That's some way we have designed our, or I think the example that we should take is the flower one. Okay. Okay, let's say we came up with some model in which we are computing theta dot t, theta dot x, which means all the weights we have computed, and using the weights, we are given the value of x, we are computing y, meaning given the value of all the weights and all the value of the features, we are computing the value of the target label, right? So that will be a number generally. So whether whatever problem that we are trying to solve, either it could be, say, classifying email into spam or something else, right? So we will basically prepare a set of features out of the email. Set of features, how will we prepare? we will basically prepare the set of features like how many times uh, how many times particular word has occurred and so on, right? So maybe the feature list could look like the top 100 common words. Okay, so each common word is becomes like a column, and that could be one of the feature way. Okay, so there are many ways actually to consider in case of natural language processing. Converting the text into features is generally a very tricky game, and there could be many features. So coming back to it, so here let's say we have, after applying the theta, as in after passing through the model, we got some number, let's say -5. Then we pass that number to sigmoid function and we get 0. That means the email is not in spam, and we say that the outcome is negative, correct? And then when it comes to here, when it comes to here, here again, there is a slightest possibility of it being on the other side, as in this much possibility. Okay, uh, and okay, so that way. Now, the probability of it being spam is here 0, then here is 1. But here it's little bit there, correct? So, and then here it is little bit higher, and so on, correct? So as we are approaching this zone that you see here, okay, this zone that you see here, there is always some amount of possibility for the left side or right side, correct? So here till say t equals -1, there is a possibility. This much is the possibility of it being on the on the it being 1, right? So and on this side, okay, it is greater than zero point 0.5. So we generally say when the possibility is greater than zero point 0.5, we say 1, and so on. So sigmoid function is is uh, is a little bit more decisive than the normal functions. I'll show you how. Okay, I'll show you how. Imagine that we basically did a standardization normally, correct? So our equation would look like, our equation will look like this. Oh, it did not work, right? Let's say we converted these numbers into something like this, correct? By using string. So what's happening is here also there is a possibility of something being 1. So this function is not decisive. The and if you talk about the extreme the case, let's say we converted these numbers into something like this, okay, into a line like this, okay. So at every point, this function, whatever it is, it's converting, say, t into a probability. So this function, which is returning some value here. So whenever you put a value, this value here, you'll get this, right? So for this value, the outcome you're getting is this, correct? So what's happening is this, whenever you ask this function for each value, it's saying 50-50. Okay, that means it's eternally confused. Okay, so it's not decisive. Therefore, the functions like sigmoid, it's basically, it's when the t value of t is lower, it's very clear that it must be 0. If the value of t is higher, the answer is 1. Okay, so it's quite decisive when it comes to converting uh, converting a decimal number into something between 0 and 1. That's the reason why we use the sigmoid function. Okay. Question is, are there any other function that has a behavior close to sigmoid function? Yes, there could be many other functions that could have a similar behavior. Okay, that could have a similar behavior. Okay. So here, let me just think of, say, some of the functions. What can we do? Let's say instead of, if t is going negative, then this will be here, and okay. Mm, I think we can come up with more such functions. Okay, we can come up with more such functions, and okay. Um, how can if something is really negative, then it should go 0 and so on, right? So there could let me just think about something if I could come up with. So you could have, okay, okay. Yeah, I'm not able to come up with something right away, but theoretically there could be many such functions. Okay, so the sole idea is that the function needs to be decisive for various values of t. It should be able to clearly say whether to go for 0 or for 1. Okay, as much as possible. The this area where there is little bit confusion, for example, when t is 0, this function always says 50-50, right? So here, that's just single value. At that point it's saying that, but for other value it is basically here in this boundary, it's a bit, you know, uh, talking fuzzy. So if this area where it's saying for this value of t, it could be a little bit positive and so on. If this region becomes thinner and thinner, that's the core idea behind having a good logistic function. Okay. Now, a question from Noor: where can we get more information on feature creation on the topic? Okay, so you mean if it's a text, then how would we convert it into features? So I think we could have a small session on natural language processing. I could walk you through the various libraries such as uh, GenSim and others, which basically convert a text into a set of vectors, which you can utilize, right? And then word to vector is there, word to vec is there, and so on, right? So you could use those kind of libraries. So basically, there are these wonderful set of libraries which can convert a word into a fixed set of features, like fixed list of numbers. Say, say there is a king. If you take a look at, okay, I'm just taking a bit of deviation. I hope that'll be okay with all of you. Okay, now, okay. So what we have so far learned is basically manipulating the features using regression. And if we could convert the word into and there's something called glob vectors. So these are generally used libraries to do that. Other than so say for example, not this, uh, the glob. Yeah. So this is one. All right. So the glob vector, basically, what it does is say given various word, what they have done is they have gone through Wikipedia and other text, and they have mapped each word to set of numbers. Okay, so you could do a lot of fun with it. And where is the okay? So these are a couple of libraries. One of them is Stanford NLP, and other is Spacey. Not this. S- s- What was the library that I was using last time? That was really good. Yeah. So these are the couple of libraries that I was using, and yeah. So I'll just put you these link to you, and these are basically couple of libraries that people generally use when they do the NLP. Okay. Right. Okay. So Glob Vectors is one of such really good tool. What it does is it converts each word into a set of numbers. As in converting each word, say frog is there, frog will be converted into a number, right? So the distance between various species of frog would be really small as compared to the distance between human and frog. Okay, so that's what it is trying to do. So with this, when you have converted each word or each entity into set of numbers that truly represents the behavior of that particular entity, then you can do rest of the linear regression just like usual one. Okay, so similarly, in case of email spam case, what you can do is you could represent each email with set of numbers. Okay, and maybe do a dot product of all those numbers to convert each email into a set of features. Okay, so that's the kind of thing you do. And glob vectors are quite powerful in that sense that basically each word is converted into numbers that truly represent the behavior of that entity. Okay, meaning that if you mathematically, there is a more fun, there's something called here, there was really fun thing. Okay, say for example, okay, okay, let me just explain what it means again. So let's say the things that we have understood is that if we would have set of features and there will be various columns. So if we could convert, say, king into a set of numbers, right? Something like this, and queen queen also into some set of numbers, right? That this is basically glob vectors. So glob vectors basically is a huge data. You can download it and then use it. Now we have the glob factor of man as well, right? Something like this. And then there is a glob vector representing woman also. Okay, so like this. So you'll be amazed to know that if you say king minus man plus woman, the outcome is very much equal to woman, not woman, queen. Okay, so this is very much equal to this. So this is a kind of fun you could actually have with these glob vectors. All right, and because each glob vector represents the true entity of true meaning of an entity. So it, so you could convert your natural language processing tasks in case, let's say, you're working on email classification, other parts. Then you could convert the text two numbers using either glob vectors or using word2vec. Word2vec also does the same thing. And then there is gensum and others. All right. So that's pretty much. Okay. Did it make sense to you? For others? Yes, that's right, Pavan. So glob already has vectors for most of the English words. Good. So a lot of NLP tasks can be, again, the way we are converting our classification task into linear regression. In the same way, a lot of NLP tasks can be converted into the linear regression by using the word2vec or glob vectors. That's right, Kamal. And synonyms would have very close value. Correct. A question from Pavan: how to evaluate situations, context where word is used? Now, that context recognition is itself a really big problem, a big deal. And I think that we maybe when we talk about NLP, we can talk about that in a bit more detailed manner. Okay. Can I try without any coding and downloading? I think it is there in our lab. If it is not there, then we will put glob vectors, and I think you can try that. Okay. All right. Maybe we can install glob vectors so which could use. Okay. Okay. Sure, Noor. And let me think over it and let me plan it. And if we have okay, so all right. So yes, I'll plan it out. Okay. Great, great. So basically, yeah, I will actually go into at later point of time we could just have a separate session about NLP, and I'm hoping that will be useful to all of you because there have been some of the interesting things that we worked upon lately. One was to automating the chat or giving the chat suggestions whenever in the talk, just like the Google Hello and LinkedIn does. And the other thing that we have worked recently on was figuring out the intent of an email, figuring out an intent of an email with respect to one of the hotel booking companies. They get an email and they need to figure out whether it's for booking, cancellation, and so on. So those kind of things we recently worked upon. So we could possibly create a small session out of our learnings on that. All right, great, wonderful. But I think it'll be better to do that after deep learning because couple of papers are really good, couple of ideas are really good after we talk about deep learning because specifically with respect to say intent detection or auto reply, we used deep learning part, the LSTM and other networks, and they were performing pretty well. So I think it'll make sense to do it at later point of time. All right. Okay. So a question from Binta is, when will we start deep learning? Just after machine learning. And the time, as I told you, has become 2x. We were not expecting to go into so much details, but we decided to go into so much details. So it's going to be, it's going to, I think we have updated the date of deep learning on website, and right, it'll take maybe at least um, 5 to 6 more weekends. Okay, to finish machine learning. I hope that's not okay. That's okay with you, because we want to do it properly. We don't want to just make you memorize everything. Instead, we want to work together on this. All right. All right. So let's go ahead and continue where we were. The point that I was explaining was that sigmoid function converts any value into 0 or 1 or something in between. The advantage of sigmoid function is that it doesn't require the entire data set to do that. It can just convert any value. The The other advantage of sigmoid function, specifically in case of logistic regression, in logistic regression, we need to convert anything into 0 and 1, right? So, and sigmoid function has a tendency to give us clear, you know, it is not, it doesn't keep things on the boundary much. Only this area it's keeping on the boundary. Otherwise, it's either saying 0, meaning no, or yes. And here it's saying maybe this is 20%, maybe this is 40%, and maybe this is 60%, only in this region. So this area is really small, and hence logistic regression can be really well performed with sigmoid. So only thing after this we need to do is we just need to check if the value is less than 0.5, then it's 0. If value is greater than zero point 0.5, make it 1. That's second thing we will do after sigmoid. Okay. So what we learned just now is that we compute the probability by using the hypothesis function, and our hypothesis function has one extra function on top of what we had earlier, right? So here we multiplied weights with numbers, and right, these are various values of features, and we multiplied that with theta, and we got some value here as after summing it up, and then we did sigma on it, right? And please note that both this and this are vectors, therefore they represents all m data points. Okay, so this probability is again a vector. It's a probability of each of the instance of x. Okay, and so sigma basically returns the probability. And then what we do is we say that if probability is less than zero point 0.5, then our outcome is 0. If greater than or equal to also is considered as 1, right? Just like we do the absolute, then just like we do what? The floor, I think, or roof. There is in maths, there is a function called floor and roof. This is where we compute this. It's a classic logic of rounding off. All right. So this is how it looks like. If you combine both the things, this is how it looks like. Is it clear to everybody? I hope it doesn't look like too much symbols. So we had thetas as in, so we represented every record as set of theta 1 into x1, x2, x3. x1, x2, x3 are the features. So, and so on. All right, good. Now that's what it is. Okay, so basically all we are trying to do is we are trying to compute the value of y passing through sigma to make it a probability. Then further we are applying this. Here we are saying that if y is the probability is lesser than 0.5, the outcome is 0, and so on. All right. So here we are trying to kind of convert this into a coin toss. Okay, we are converting this into kind of a coin toss. Coin toss is wrong word to use because that's totally random. Here, it's very clear. Okay, so essentially the idea is to convert number into 0 and 1. Okay, discrete values from continuous values. Okay, now that's how we would compute the outcome. Now question is, how do we, let's detail out how would our cost function would look like and how would our training would look like. Let's understand how to train a logistic regression model. The objective is to of training is to set the parameter vector theta so that model estimates the high probability of for positive instances and low probability of negative instances. Okay, so meaning when so all we are going to do in this training is we are going to find those thetas for which for which the we are going to find those thetas for which we get high probabilities when the right hand side is 1, low probabilities when the right hand side is 0. Okay, so we're going to compute those thetas. That's all. All right. And further, what we can do is we can convert the probabilities into log. Okay, this is the cost function that's going to be, because what we want is our cost function should always, we should always minimize the cost function. Okay, we should always minimize the cost function. So the cost function looks like this. Cost function is a function of the two instances. Okay, it's a function of two instances. If the right hand side is 1, our cost is this. If our right hand side is 0, our cost is this. Okay, let's take a look at this. If let's say let's take a look at the outcome here. If the p probability is between 0 and 1, right? So the cost is going to be, if the y is 1, if y is 1, our cost function is this. Okay, so if the y is 1, the cost function is going to be like this, which means that if probability is between 0 and 1, here, this is how the cost is going to vary. So the overall objective is to minimize the cost. At the minimum cost, we should get what we are looking for, correct? What we are looking for is y equals 1. So at minimum cost, we should get 1, correct? So if on this side, if at very low values, so here the probability is really 0, the cost is going to be tremendous. The cost is going to be tremendous. Okay, that means this is something undesirable. This is something undesirable. This is what is desirable. So what we do in case of training is we minimize cost. So the cost function, so it has, strangely, it has two cost functions. One is in the logistic regression, we have two cost functions. If the right hand side is 1, as in our label says 1, the cost function is going to be log of the probabilities and then minus 1 multiplied to it, correct? So what we have here is the curve that kind of shows that how the cost would vary with the probabilities. Okay, so if the right hand side, the label is 1, the cost is going to be tremendous if the probability is low, correct? That's what we want. We want the probability, if the probability is kind of equal to 1, we want the cost to be 0. Okay, similarly, if the y is 0, the right hand side is 0, the cost function is going to be different. Okay, here all we are doing is we are just putting 1 minus probability. So here again, if you take a look at it closely, when the probability is really small, right, the cost is going to be small. If the probability is going higher, okay, that means it's going, cost is going higher. That means we would want this side here and this side here. Okay, so we will have to find those thetas. We'll have to permute, or we have to find or regress over those thetas where the cost is small. Okay, if the right hand side is 1, the cost is going to be this. If the right hand side is 0, the cost is going to be this. Okay, so basically, all we are trying to do is minimize the cost. All we are trying to do is minimize the cost. All right, so that's what we have described here. If y is 1, as in right hand side is 1, and the probability is 1, then the cost is going to be 0, meaning we are doing very good. We're doing very good if the cost is 0. Okay, so that's our cost function. So our cost function, let me just combine the cost function, that will make more sense. So here you can see that in this case, if the probability, we are predicting 0 while the actual is 1, in that case, the cost is huge. Okay, so we have to reduce the cost. We have to change the thetas such that we don't end up here. We don't, our model should not predict, should not give this probability, okay, if the right hand side is 1. Okay, our model should give this kind of probability if our right hand side is 1. Okay, so we have to choose those thetas wisely which minimize the cost, and hence this kind of function. All right, so similarly here, this is what we want. This is what we want. This is the side where we would like to choose those thetas where cost is really low. Okay, now if you combine the two, this is how it's going to look like. Okay, so the cost function is going to be, for each instance, for each of the m, it's going to be y, which is right hand side 0 or 1, and this is the cost function in case of this. In case y is 1, then this cost function comes into play. If y is 0, this cost function disappears and this function works, right? That's how it is. Okay, so let me just try to demonstrate that. Okay, so if you take a look at this portion, right? Okay, so what is this? This is basically the cost, correct? This is the cost, overall cost. So how are we computing cost? So we had let's say some, right? These are our, this is our x, and there would be some sorry, this will be our theta. Okay, and then there will be x's and so on, right? And this is our y. So what we are saying is, if y is say 1, okay, y is say 1. So if y is 1, so only this portion will remain visible. This is for y equals 1, correct? Y, sorry, this is for y equals, okay. Okay, so this is for, if y equals 1, what will happen is this will become 0, right? If this becomes 0, the whole function disappears. Okay, so this whole function would disappear, and therefore the cost function would only have this term, right? So if y is 0, what will happen is y is 0, it will multiply with here 0 multiplied by the log of probability, and therefore this term will disappear and only this term will remain, correct? So basically whatever we just told here, whatever we have told here, this condition is represented like this. Okay, the same condition, this cost, see, for each instance, the cost that we're talking about, the cost that we're talking about is y into y into log of p, okay, log of p plus 1 minus y into log of p, correct? So this, okay, so this, what you see here as a condition, like saying um, the cost for each instance is minus log p if right hand side is 1, minus log of 1 minus p if the right hand side is 0. So same thing could be written here. Same thing could be written like this: y log p and y into log p, right? So what does it mean? If y is 1, what will remain? If y equals 1, the cost function will become only this, right? If y is 0, then the cost function will remain. So just that there will be an extra, you can put one extra minus here. Okay, we'll just put one minus here. Okay, so this is how it will look like. So if y is 0, what will happen is this will be minus of, sorry, this will be 1 minus p. Okay, the cost will become log p and this. Okay, so does it make sense to you now? So for the cost of each instance is computed like this. The the value of each label multiplied with log of the probability. And how do we compute the probability? Using the logistic function over sigma over theta dot x. Is it clear to everyone? And here all we are doing is summing it up, summing all the costs, okay, and divide by m, meaning computing the average cost. So for every record, or for every record in the data set, what we're going to do is, or you can say every record in the training set, for every record in the training set, what we're going to do is we are going to compute probability. Okay. So for every record in the data set, what we're going to do is assume initial value of thetas, compute the x, okay, for assume the value of theta multiplied with the feature values for each record, and then compute the cost, okay, and then sum up the cost over all of the data sets, all of the records in the data set, and minimize that. Okay, minimize using your standard algorithms, whatever we have learned, whether gradient descent or stochastic gradient descent or mini batch. Okay, is everybody on the same page? Abhinav, Balaji, Bintao, Gigi, Kamal, Noor, Pavan, Pratik, Shahrukh. So this is our cost function. So feel free to ask, because this looks like too much of maths to you. Please feel free to ask, because it's pretty easy actually. It's just that there are too many symbols, so it looks little sleepy. And okay, so Noor's question is, these slides are missing there. Let me just see if I could No, I think these slides should be available. I can see that anonymous users are accessing it. Go to the 280th slide, okay? Because what I remember is I had shared with you the entire one, so it should get reflected as soon as something happens there. All right, wonderful, wonderful. So, okay, not clear to Pavan and Binta. All right. Okay, please feel free to ask wherever you get doubt because that's the only way to learn. Okay, the chances are whatever confusions, doubts you have, others might also be having. All right, wonderful. Now, this is basically rest of the logic that we talked about earlier would remain the same. The linear regression, stochastic gradient descent, and so on. Everything else will remain same. Just the computation of the cost function would change. Okay, the cost function would change. Rest of the gradient descent and other methodology would remain exactly the way we had discussed. Yes. We just need to minimize the cost. So we'll compute, okay, yes. So Kamal's question is, should we not regularize this cost function the way we did for linear? Yes, we will be. We should be. Good point. All right. Okay. So yeah. So the regularization would remain exactly the way it was earlier, that regularizing term, and other factors would remain similar. Okay. So let me just go over there. Now, the other things that we that become other than our usual regression, the problems related to the linear regression, right? The things like the problems with gradient descent, choosing the learning rate, and so on. Those and regularization, though all those things would remain as such. There is some additional parts to it. Okay, there are some additional parts to it, so we'll talk about those, and then we will pick up those same things in the SVM. Okay, now let's take good example. So there is something called iris dataset. It has been there forever, and in almost every example of classification, we use iris dataset for as like hello world. Okay, so this iris dataset contains sepal and petal length. Okay, 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 let me again describe. So I'll explain what is sepal and petal. So basically this iris dataset doesn't have the pictures of flowers. It has the length of sepal and petal. Okay, these are the two parts of the flower, and it contains the length and width of both of sepals and petals. So essentially, there are four input parameters. Okay, and this dataset contains three flowers. On the right-hand side, the Y's, there are three flowers that you need to detect. So essentially, what you are given is the details of sepal and petal for each of the flowers. Okay, so each of these flowers. Okay, iris setosa, iris versicolor, and iris virginica. Okay, so those are the three flowers that you basically uh, have with all their details. All right. So question from Pavan is, its name ends with regression, but we use it for classification. So What we are doing is we are using regression, the standard regression technique for the classification. Okay, for the classification. So generally the differences between regression and classification is in regression we need to estimate a value, a decimal value. In classification, we need to uh, predict a Boolean value, true or false. That's the only difference. And the functions like sigmoid followed by the other function, all we did was we converted decimal number into a Boolean flag, okay, using those methods. All right. So logistic regression is a regression used for classification. So classification is a problem statement, and the regression is a technique. All right. So basically, these are the three kinds of flowers that we want to identify. The sepal is this part of the flower, the lower part, which holds the petals, and petals are the flowers. These are the parts that is generally visible to us. So sepals are holding the petals. Okay. All right. So a question from Pavan is, regression techniques can be used for classification, but not the other way around. Actually, the classification is a statement of a problem. Underneath, the classification is either implemented using regression, using SVM, or using some other technique. Okay, using some other technique, maybe the neural net. So classification is kind of an objective. How to achieve that objective is by the way of these techniques, using logistic regression, using SVM, using neural net, or some other technique. All right. So there's a bit of confusion in the term there. Generally, we say that the problem is either regression or classification. But the truth is, under the hood, classification is also dealt with similarly as regression in some of the cases. Otherwise, sometimes classification is also solved using some other techniques like SVM and others. All right, good question. Good question. Now, moving ahead. So these are the parts. These are part of the these are part of the flowers that we are going to talk about. So petal and sepal. All right. So this is how our data set looks like. Our data set has label and this label is between these three flowers: Setosa, versicolor, virginica. So this is, I think, 0, 1, and 2. So these are the labels. Okay, and these are the various samples having these four feature vectors. So this is uh, sepal length, width, petal length, and petal width. Okay, so these are the features. There are attributes, measurement, and dimensions. You can also use the alternative words like attributes, measurement, and dimensions. Okay, so this one is the class labels or targets. All right. So yeah, instances or observations. I generally end up calling it a record. Okay. So this is the terminology that we are going to use ahead. Okay. All right. Now, so now let's take a look at the data set. I'm going to open. Question from Gigi is that can we solve this using regression method? Yes, that's what we're going to do. Okay. So the technique and the strategy would remain just like regression, just the cost function would change. Okay. Because instead of trying to minimize the delta between the right hand side and our projected value, what we are trying to minimize is what we are trying to do is we are trying to convert the outcome into something between in 0 and 1 and then use the objective function accordingly. Okay, good question. Now where are we? So training linear models. Okay, all right, I think we have reached. Okay, so let's explore the data set. All right. And right, in case you want to take a look at how to plot this graph and how to compute this, you could just use this is our sigmoid function. It's pretty straight, right? So np.exp and so on, right? All right, so this is how you could plot it. Yeah, thank you, Noor. So that's what we'll do. We'll just go to the home folder. Let me also show you. New notebook, not new notebook. I'll just go back here, say new terminal. And there I'll say git pull, cd ml, cd machine learning. I'll say git pull. Oh, sorry. And does it not work? Git pull. Oh, I need to see git pull origin master, right? Yeah, it says already up to date. Good. All right. So what we have is let's take a look at this data set. Okay. And we are importing from Scikit-learn, we are importing the data sets. And in data set, we are saying load iris. Okay. And we say iris.keys, and it would give us all the columns. Okay. And further, we say iris.describe, .descr. So here, this is the description of the data set. You can see that? Now, so here we are. So we say print iris.data, and you have those four columns over and over. Okay. And iris.feature names, iris.target. Okay. So iris.data and iris.target is something that we are interested in. All right. Now, and the target names are these. So what we have here is we are training the logistic regression model here. Okay. All right. So sure, Binda. Let's see what all can we specify here. So what we have here is this is our data set. Okay. And we are saying that we are just going to keep the petal width and petal length, correct? So this is essentially going to give us how many columns? Oh, we are just keeping one of this data set. Okay, so we are just keeping the petal width for now for the left hand side, and for the right hand side we are keeping the okay, we're keeping only one class. Okay, we are saying if it's this particular one or not. Okay, this one or not. So that's all we are saying, and then we are importing the logistic regression from linear model and then fitting this data set. That's all. Okay. So once we basically fit this, all right, I'll have to import numpy snp. Okay, and also I'll have to import the plot because I don't want to go from the top. There is some kind of error there. Okay, so this is something which we have, and so where is the okay, I'll just run this. That's all. Good. So what we have here is here what we have done is we have generated the model. This is the logistic regression model, and here we have already talked about things like max iteration, random state, the penalty function, and the solver is basically the linear solver. And this I'll have to take a look at which one are we using here exactly. And then we have also passed the tolerance. Okay, and we are not retaining the if we are fitting the logistic regression again and again, are we if you're calling this function again and again, should we retain the previous model or not? That is false. Okay, and so that's one thing. And yeah, so there are quite a few features. We'll go into these further again, probably at a later point of time. All right, so here let me just okay, now let's try to plot whatever we have done just now. So first of all, we're going to just generate x, then predict the values for these new values of x, and then we are basically specifying the figure size and then plotting the x. Okay, so here we are plotting basically two graphs. One is this, other is this. Okay, other is this. So, and this is how it looks like. So now then we are plotting the decision boundary. Okay, this is decision boundary, and all right. So let's take a look at our prediction. So what we have just done is based on one parameter, I think petal width, we are trying to predict the flower type. Okay, so here the flower type is basically a function of only one one of the parameter features right now. Therefore, there would be mistakes in this. So let's take a look at the outcome. So the probability of of a flower being Iris virginica is actually low here. So this is good. This is good. High here. This is also good. The only problem is here, the descent boundary. So on this descent boundary, there is the high probability of both. Okay, high probability of both. Now, let me just show you from that side. Okay, so yeah, this we have talked about. Okay, so this also we have discussed. Now, so this is the estimated probabilities that we are showing you in the Jupyter notebook as well. So what we have is on the y-axis, the probabilities. On the x-axis is the petal width. If the petal width is smaller, the chance of it being the Virginica is lower. Okay, and so on, as per our model. Okay, while the actual instances are like this. Okay, actual instances with respect to the petal width are like this. Okay, so here you can see that here at this point there is overlap. Okay, so at this point, take a look at this point. So given a petal width as 1.6, right? This would be probably 1.6. The instance could be either the Iris virginica, or it could be any other. Therefore, at this, because 1.6 petal width is common to others also, and hence we need more parameters, more features to solve this. Okay, so the petal width of Iris virginica flowers is represented by triangles, and non-ones are represented by these squares. Now, it ranges from 1.4 to 2.5, 1.4 to 2.5, correct? Now, if the other flowers, other flowers from the iris group, these are represented by squares, and the they generally have the smaller petal width. Okay, we're ranging from here to here. Okay, so basically this is our overlap. This is where the overlap is happening. Question is, how do we resolve this overlap? Okay, question is, how do we resolve this kind of overlap? Now, okay, so it's not easy to just if you when you are doing the classification, you should generally plot this kind of descent boundaries and take a look at where the overlap is happening. So above 2 centimeters, wherever the above 2 centimeters, the classifier is highly confident. Here it's pretty confident. Okay, that the flower is virginica, and as it outputs the high probability of this class. Similarly, this side as well as this side, both sides it's highly confident, but at this point you can see that there is an overlapping between other flowers. Okay, so here also it's quite confident. All right, the descent boundary is at around 1.6, where the probabilities of a flower being virginica or non-virginica is equal. Okay, so at this point, there is a this is the descent boundary where there is an overlap between others. So if the petal width is higher than 1.6, the classifier will predict the flower as virginica, or else it'll. So the predictions which it is doing here, it's kind of wrong, right? It's slightly wrong because here the probability of both is kind of equal. All right. So let's just check the prediction here. Let's just check the prediction. So for the petal width of 1.7, 1.7 here maybe, and 1.5. Okay. So here you can see that for this one, it has given as 0 for this point, while for this 1.7, it has given it as 1. Okay. So let me explain more. Now, if at this point of time, to reduce this kind of confusion, the one thing that we could do is we could include both petal width and length, and then take a look at the descent boundary again. All right. Now, since we have two features now, let's draw it. Here there is we have tried to draw it in a very neat fashion. So here on the x-axis we have petal length, on y-axis we have petal width, and what you see is these are the various data points. These are the various data points or instances, and these are various instances. So you can see that it is very much clear as compared to the previous scenario. Earlier, there were many instances between the descent boundaries. Okay, so all right. So here, this is where we are trying to predict. All right. Let me show you again. So this is, let me just walk you through it. So here is the logistic regression that we have imported. Then here we are picking up these two petal width and petal length. Okay, let's just take a look at this independently. You can press A to just insert a cell. So you can see that this time we are picking up two features instead of one feature. Earlier we had only kept a single feature. Now we further compute Y. Okay, then we compute the logistic regression, and then we create an instance of a function called logistic regression, and then we fit it. Afterwards, we are just trying to do the number generation here. Okay, and just so that we can plot the graph. For these new values, x new, that we have just generated, we are predicting the probabilities. Okay. So question from Minda is, what is C equals here? So C is equals something called a descent boundary function. So we'll talk about descent boundary in a while in the next session. And this part we will cover in detail there. Okay. So it's for now, you just consider it just another hyperparameter. Okay. So this generally, if this is really huge, that means the this distance is going to be lower. So we'll go into more details as we proceed further. Okay. So we'll go into more details about this. So for now, you can just think of it as another hyperparameter. All right. So once we are done with that, then we are predicting for the newly generated numbers. So here we generated x naught x1, created new x. This is the for the graph. Then we predicted y for each of x. Okay, and then we are plotting the plot afterwards. Okay, So this is how it looks like. So what you see here is that this time the separation is very clear. This the line that we are drawing here is between these two instances. Okay. So a question from Inta is what is -1 in reshape? We're converting a, a entire row into the column. Let me just show you what it means. Okay, this one, right? So I'll show you. Let's take a look at this. Let's take a look at this. So here we are saying that we are saying this. So it's starting from 2.9. Okay, it'll go up to 7, and we are saying 500 points. Okay, meaning there'll be 500 records. Okay, because in this data set we have 500 records. So the next thing we are doing is we're converting this. What you see here is this. Let me just put it as okay. So we are converting this huge single dimension array into two-dimensional array with instead of one row, we are creating one column. Okay, instead of one row, we're creating it as one column. All right. Good. Next, we are plotting it, and this is how it looks like. Yes, kind of transpose. You are right. But you can't call it transpose because that one is a one-dimensional array and the resultant is a two-dimensional array. So we can't transpose just like this. Okay, that's the reason. So question is, what is mesh grid? Mesh grid is essentially combining the two. Combining the two. Okay, let me just show you. Okay, if you take a look at this, it's essentially appending the two values. So you can see 2.9 and 0.8. 0.8 is coming from x1. 2.9 is coming from x0. So sorry. So this and this. These two columns are being added to this one. So this 2.9 is coming from this 2.9 is coming from the first linear space, and this 1.8 is coming from this. Okay. So basically, this is like appending columns. Okay, then we are converting this, giving it to x0, x1, and then, okay. No, actually, the mesh grid is doing something else. Mesh grid is doing something else. Yeah, I'll show you. Mesh grid is actually, the concatenation is happening here. Concatenation of column is happening here. Mesh grid is doing basically, if you take a look at the x0, all right, so this is something that's happening here. Okay. Okay, so it's actually kind of the mass grid is basically for every record in the first side is joining with the second record. So it's more like generating the generating repeating each of them, repeating each of them. So if you see length of x naught is 200 and length of x1 is 200. Okay, okay, okay. All right. Yeah. So essentially, how should I describe this? So what is this? This is a single column vector having 500 values, right? It has 500 rows and one column. Similarly, this one is having 200 rows and one column, correct? Now, what MeshGrid is doing is it's basically repeating this, repeating this. Um, I think 200 times, so that the resultant is having say only 200 values. So that way. Okay. Okay. So the core idea is that we generate the data set which has a length of equal to the multiplication of both. Okay. So this is the way it is. So 500 into 200. So that's the record. All right. So essentially, it's kind of doing the multiplication of the repetition of one record with another record. That's all it's doing in both the cases. So for each value of x now, for each value of this, it has generated this. So that's what it is. Basically, it's kind of joining the two data sets. And you can see that the resultant value, the x new was having uh, x new was having the 100,000 records, which is 500 into 200. Okay, I hope that makes sense to you. It's basically cross join. Yeah. Okay. This is essentially for plotting these graphs. So for each value, we have tried to plot it. Okay. So one of the values we are generating from where? We are starting from 0.8, other 2.9. So from here to upwards and from here to upwards. So that's what we're doing. All right, so what we have done is we have generated all kinds of data points. Then we have plotted that, and this is how it looks like. Okay. Now, so again, if you want to use the softmax that we had uh, talked about earlier, using the I mean the softmax function or logistic function that we talked about, that sigmoid function, then we could use LBFG. Yeah, LBFG. Let me explain what is LBFG. That's what is coming next. Okay. After this, let me just explain that. So what we saw in the graph was the boundary was linear. Okay, meaning the separation between, if you plot the graph petal width and petal length like this, if the line that is separating the two instances is a single line, it's not a curve, then this is called linear decision boundary. Okay, it could have also been a curve, or it could have been really complex, but here a single line is able to separate it. This is called linear decision boundary. Okay, so the dashed line here are the points. This dashed line is the line which is representing the points where the model is estimating the probability, prob estimating a probability as 50%. Okay, meaning at this point, it could be either just on the decision boundary here, here, or here. If some flower has petal length of 5.5 and petal width of say 1.75, 1.3. Okay, then if some flower has this, then it could be either this or this. So this is decision boundary. Okay, each parallel line represents the points where the model outputs a specific probability from 1.5 to 90% in the top right. So here, the bottom right, bottom left, from here to here. Okay, here the probability is 50%. Here the probability is little lesser than 50%, and so on. And here the probability is close to 100%. So that's what is the significance of this kind of a graph. Okay. All the flowers beyond the top right line, all the flowers beyond the top right line have an over 90% chance of being okay. So yeah, that we have already talked about. Now, so like linear models, logistic regression models can be regularized either using L1 or L2. Okay, just like the way we did in linear regression, we could also use either of the two penalties. Essentially, either we could either use the lasso or we could use ridge, right? We could use ridge, L1 is ridge and the other one is lasso. So the scikit-learn by default adds L2 penalty by default. Okay, and all right. So that's the important part. That's what I was talking about in the beginning. So the regularization basically remains the same way. Okay. By default, it's L2. You could also put L1. Okay. So the logistic regression model can be generalized to support multiple classes without having to train and combine multiple binary classifier. This is called softmax regression or multinomial logistic regression. Let's do a quick hands-on on softmax regression before going into theory. All right, let's jump into it. Okay, so what we're going to do is okay, using softmax regression. So again, what is softmax regression? Softmax regression is, okay, let me step back and discuss what we had already discussed. So when we were classifying digits, the handwritten digits, you were classifying them into multiple buckets, right? And how did we do that? By using the classification multiple times. There were two approaches we talked about, one versus one and one versus all. Remember? So we create so many classifiers and there were two approaches to create many classifier. One was one versus one and the other was one versus all, right? So, so in case of softmax regression, in case of softmax regression, we are we're going to um, basically do that in a single class instead of in a single shot instead of creating so many classifiers. That's the idea behind softmax regression is. Okay, a question from Noor: where did we calculate the cost? The cost was calculated by this logistic functions, this logistic regression internally. Okay, this logistic regression is calculating the cost internally using using a function that we talked about. Using, where is that function? Using this, it's computing the cost internally. All right. So what we learned just now is we were able to classify the flowers, or at least the Virginica versus non-Virginica. Just and we also noticed the decision boundary was linear when we plot it like this. Okay, the decision boundary was linear. Okay. Now, we're talking about something called softmax regression, whereby if just now what we did was we converted our problem into a very simple one where right-hand side was only one column, as in it was only true or false. Had it been either things like we are trying to predict multiple flowers, then we will need to do the either we combine multiple binary classifiers the way we did earlier using OVO or OVA, one versus one or one versus all, or we use softmax regression. Okay. Okay. So here, when we were using logistic regression, the same function, all we do is multiclass is multinomial, and here we could say solver is LBFGS. Okay. So okay, so here we are saying that pick second and third feature. Y is the target, and then we are using this. And again, the same hyperparameter C is basically the decision boundary hyperparameter. It decides how big the decision boundary has to be. We'll talk about this in a while. Okay. Now, once we have fitted it, then we can do that. Okay. So LBFGH is basically named after these the researchers, and it's an iterative method for solving unconstrained non-linear problems. Okay, so C is the hyperparameter for regularizing L2. Okay, now let's take a break for 10 minutes. Hi everyone, I'm back. So should we start? Okay. A question from Bintao is that will we have class next week? So we will have class on Sunday. The Saturday one I'll have to um, cancel because the set on Saturday I have a boot camp in Singapore. So so that's why I'm thinking of canceling because the time will overlap. I was thinking that since in case of Singapore, right, the 8 a.m. for me is the 10:30 for them, and therefore the time will overlap, and I'll have to cancel the class. And okay, all right. So great. Hi Balaji, Bintao, Gigi, Kamal, Noor, Pavan, and Pratik, Abhinav, and Shahrukh. So should we start? Wonderful, wonderful. So great. Now the logistic regression model we had talked about. So we learned today, what we learned today is that the classification could be modeled using the same regression models, same linear regression model, and that's what we call it as logistic regression. Okay. By the way, logistic regression, specifically the ones that we talked about today, is a common interview question, and then you have to basically you just have to explain that it's the same regression, just the cost function is different. And the cost function is something people do ask when talking about logistic regression model. Okay. The other very interesting question that people ask during machine learning is the regularization. And the next one is with respect to hands-on, people generally ask you to do if you are being hired for a data scientist position, you might you might get asked to implement the gradient descent. Okay, so anyway, we have started this chain of blog posts, okay, where we will be publishing the common interview questions. So if you go to cloudxlab.com, go to blogs, you will see that. Okay, and all right. So, or you could come over to the forum and start asking questions. And if you are, I think most of you can start interviewing for machine learning kind of positions right now. Right now, also, a lot of things that we have discussed is actually equivalent of the usual machine learning course, whatever we have discussed so far. And what we're doing now is we're going deeper down into each models. So you can actually start interviewing right away, so that you can also get an idea that what kind of things you need to prepare for. Also, we are going to publish it in more details on our blog post in the coming weeks. All right. So this whole idea is to help you with respect to the interview questions. Other important interview question that people generally ask is how does what does it mean by cross validation and how does it happen? Okay. All right. So the softmax regression is another very important topic. Okay. So whatever we learned in logistic regression can be generalized to support multiple classes without having to train and combine multiple binary classifiers, right? So either we could use the technique that we used earlier by combining multiple binary classifiers, or we could use the softmax. Softmax is also called multinomial logistic regression. Okay, so let's just take a look at. Okay, uh, all right. A question from Noor is, the main thing about interviewing is to provide some kind of experience. In your opinion, how can we achieve that? I think this session is going to be more than 4 months. Okay, so you could actually write this as experience in your CP. That would actually help you in, and then okay. So the experience with respect to this would actually help you because it shows that you have gone through a rigorous detailed course and solved some amount of the thing. The other thing I would suggest is that you should solve a couple of Kaggle problems. That is actually very useful in the career. Okay, the Kaggle problems, GitHub repository, and mentioning the CloudX Lab as your experience in the CV. Okay, as in but you can write it as a education experience in which you did these projects. Okay, so that would generally help you in getting the interview call, and then rest of the interviews you can definitely handle. All right, and good. So I think I should just detail out on a blog post. So let me uh, write a blog post in detail further. We have already written a lot of questions. I'll also write these other parts. Now, The this called basically the softmax regression is what we're going to just do a hands-on. Okay, so this is pretty simple, just that we are using the multi-class as multinomial, and the solver is this. Okay, these are the two changes that we are doing. Okay, and right, let me just run it. So here, let's take a look at X first. Okay, so the X is only the features, these two features, and let's also take a look at Y. What does Y look like? Okay, so Y basically looks like this. You can see the value of Y is going from 0 to 2. All right, so basically on the right hand side, instead of 0 and 1, this time it's 0, 1, and 2. Okay, and here we are saying that this is where the multi-class comes into play. Okay, to solve such kind of thing, we are using the multinomial, and the particular algorithm that we're using is LBFGS. Okay, and if you want to see we want to predict something, we can quickly predict. So basically, for a 5 centimeter long and 2 centimeter wide petal, our answer is 2. So it's able to predict. Okay. Now, what what these regression models also provide is that they can give us the probabilities. Okay, not only the actual prediction, but the probabilities. Here, the probability is for given the same petal, same petal. Here we are providing same petal and asking for probabilities. It's telling us these three things. Okay, the probability of this one, probability of it being in the 0 is this, probability it being in 1 is this, probability it being 2 is this. Okay, and and therefore this one is the highest. It is 0.9. Okay, this is 0.9, this is 0.05, and this one is 0.00006. All right, so therefore this one is the one which is most probable, and hence the result is this. Okay, a question is, what does 0, 1, and 2 stand for? How can I check? So if you go up a bit, there we had talked about something called iris.target names. So iris.target gives us this data, while iris target names is this. Okay, Setosa, versicolor, and virginica. Okay, so and the way you can remember is that this is in alphabetic order. Therefore, this means the virginica. All right. So this is basically the softmax regression. And again, softmax regression will again be used at many other places as we go into say deep learning and other parts. All right. So it is named after softmax regression is an alternative method for solving unconstrained nonlinear optimization problems. It's basically named after these four researchers. L stands for logistic and BFGS algorithm. Okay. Now, so yeah. So it's basically giving us the probability of the Virginica as the highest, while the probability of versicolor is 5.8%, while this one is really small. Okay, so let's try to understand how does the softmax regression work. In softmax regression, give, given an instance X, softmax model first computes a score Sk for each of the class K. Okay, then applies the softmax function to the scores. Okay, so what it does is it For each of the class, it computes the theta. Okay, so each class has got its own vector of theta. So essentially, the thetas are separate for each class. And then it computes the softmax score here for each class. And then what it does is it computes the sigmoid function like this. Yes. So class equals label, that's correct. So class and labels are going to be used interchangeably. Records, instances, and training record instances are something same. Attributes and feature, we will call them interchangeably and so on. Okay. Now, coming back to it. So the softmax score class for theta is this and so on. Now, the overall probability for all the classes, overall probability of the classes is computed like this. For each class K, the probability function is e to the power, the same function what we talked about earlier. Okay, let me step back and explain what we're talking about. So, there was a nice table. I would like to walk you through that again. Yeah, this one, right? So here, class or targets, both class labels and targets are something same thing here. Okay, Anur. And these are the samples. We call them training sample or testing sample. Each record is called instance, observation, and sometimes a simple record. And the features are also called measurements, attributes, and dimensions. Okay, so that's the. All right, so keep moving. Now, so basically in softmax regression, given each instance, what we do is we compute the softmax model, as in the softmax model first computes the score sk for each class. What it does is for every class, it assumes certain theta values. Okay, and then it computes the score for each class for each record, and then applies the softmax function to the scores and use that as the as the cost function. Okay, now so once we have score for every class of instance x, okay, then we can estimate the probability pk using the softmax function. Okay, this is the softmax function. So here we are saying that probability of a record x being k is equal to e to the power this, whatever we have computed here, divided by summation of all of the values. So this we will compute for each class. For first we'll assume certain values of theta, and then based on those thetas for each of the classes. So if there are, say here in our case is 0, 1, and 2, there are three classes, 0, 1, and 2, correct? So we'll compute something called for 0, then 1 and 2. So there will be three theta vectors, three what do you say, parameters. And all these three, what we are going to do is we are going to compute sk for each class. Yes, sk for each class. All right. Yeah, that's right. This k is same, as in k means total count. Okay, total count of k's. So here t is for transformation, transpose. Okay. Yeah. So all right. So what we're going to do is we are going to compute this for every class, then sum all of them, and divide this value by all of them. So it's like this. So just the difference is we are putting e to the power something. Okay. divided by summation of all these values and so on. Okay. So we are computing the values of well, the softmax score for each class, and then uh, softmax score is usual values. Okay, usual values the way we compute, just that it's being done for each class. Now we what we do is we compute the softmax function like this. We say e to the power the whatever we had done earlier divide by total of the all. So we compute this for all the classes, and then we sum up by doing e to the power the value that we computed earlier, and then we compute this. So once we have the score for every class, then we estimate the probability pk using the softmax function. So we are saying that this value this value this value divided by the total value of all the classes. Okay, and so this is the probability of an instance being being in the class K. Okay, so probability that instance belongs to the class K is this. So softmax function is essentially estimating the probability of a particular instance, a particular record being in the class K. Okay, so we do this for all of the Ks. Okay, we do compute this softmax function for all of the classes, and that's what for all of the records, and it basically computes the exponential of every score and then normalizes them by summing up all the exponentials. Okay, okay, so here K is the total number of classes. Sx is the vector containing the score of each class of instance X. Okay, so S is a vector containing the score of each class, and the sigma is the estimated probability that instance belongs to K class. Correct? Now, so let me go back. I think I need to show you the data set again. That is important. I'll just get the data set here so that we okay. So here we are. So what we are trying to do is for each of the instances, we are computing for each of the instances and for each of the classes. Okay, we are computing this theta. Okay, so we are assuming certain value of theta, then multiply by x, and therefore there will be three separate values. Okay, three separate values. Now we are summing up all those values. Okay, so we assumed three set of thetas. Okay, theta is nothing but the coefficient of this, coefficient of this, coefficient of this, coefficient of this. Correct? So plus one bias. Correct? So those five values will be thetas here. Correct? And what we are doing is those five values we are assuming one set for setosa, other set for versicolor, other set for virginica. So we got how many? Three theta vectors. Okay, we got three theta vectors. Now, what we are going to do is we are going to compute e to the power e to the power e to the power sk. And what is sk? Once we have computed the thetas for all of these, we have let's say we'll assume it first, and then we multiply it there. So we'll get three sk values, three s values, and then what we do is we do the e to the power of all the three. Okay. Now we get some number. Then what we're doing is we are computing the summation of all the three. okay, summation of all the three, and dividing each one, okay. So once we have the score for every class X, then we can estimate the probability P using the softmax function. And then the probability, this P means the probability that instance belongs to the class K. Okay, that's the probability. Okay, and it computes the exponential of every score and then normalizes it. Okay, now softmax function calculates the probability of each target class over all possible target classes. It returns the probabilities of each class, and the target class will have the high probability. Okay, so the calculated probability will be in the ranges of 0 to 1. The sum of all probabilities is going to be 1, and it is used in multiple classification logistic regression model in building neural networks and so on. Okay, so essentially the softmax function, using this softmax function, we kind of create a cost function. We create a cost function and then we optimize it. All right. So it is a slight optimization. It is a slight optimization on our OVA, one versus all. In one versus all, there were little more computation involved. While in softmax, we are, instead of doing everything 3 times, here we are just keeping the 3 set of thetas, but most of the computation is shared and is faster. So, all right. So that this is what we are trying to do. So we are trying to, at this point, we will be trying to maximize the kth, the probability of k class, whatever is the current class, and minimize the probability of others. Okay, so that's what we are going to do. So essentially, softmax function is good for multi-class classification using the same linear models and without having to do OVA. And the way it works is by computing the probability of one instance and then maximizing that probability, but by using the similar minus log p kind of cost function. Okay, so this is basically the softmax function. All right. So softmax function will be used again, softmax as well as logistic, all of sigmoid and these things will keep on coming again as we go ahead. Right. So that's pretty much with respect to training model. I would like to now continue with the SVM. Any questions with respect to softmax? No? No questions? A question is, if the probabilities are too close, then how it is going to decide? Okay. All right. Okay. So question from Noor is, if the probabilities are too close, then how it decides? Okay, so yes, that's the decision boundary. And in case, let's say when we are taking these calls, right, here, right, if the probabilities are too close, too close, as in when we are doing the separations and the probabilities are too close, then generally the general thumb rule is that if it is lesser than 0.5, classify at 0, otherwise classify at 1. That's the general thumb rule. But if it's happening for a lot of instances. The probability, a lot of instances are on the boundary or decision boundary, then there is something seriously wrong with our data model. Okay, it may be nonlinear. It may be that we have not figured out a proper model yet. Okay, so that could be the possibility. if if let's say here, right, there were circles, right, the triangles could have been inside and the blue ones were outside, so let's say concentric circles, it would be impossible to use this kind of model. We might have to use some other complex model instead of taking up the linear models. Okay, a question from Kamal. Softmax model first computes the score, yes, as k for each of the class K, correct? Okay, this is the SK. It is not the sigmoid function. All right. So this is not the sigmoid function. Okay. So yeah. So all it does is in the beginning. Okay. So at the end of day, the probability. This is the probability. Okay. So if they are on the right hand side, let's say we take a instance, first instance. Okay. So let's take the first instance. If we are training on the first instance, the setosa is 0, correct? Setosa belongs to 0, 1. So P will be 0 here. We are computing the probability of this P equals this. Okay, so at every instance, we will have thetas, correct? Every instance will have thetas. One set of theta for setosa, other for versicolor, and a third one for virginica. So all three classes will have three set of thetas. Now we multiply this theta, uh, the thetas here for each one of them, and then compute the SK. Okay, for all of them. Then we compute the denominator, and the numerator is only corresponding to the class which is here. Okay, which is there. So we compute that probability. We compute the probability of this being there, and then we maximize this probability. The cost function is going to be logarithm of this. Okay, logarithm of this, and that's how it is going to be. Okay, correct. So softmax function is a substitute for sigmoid in multiclass. That's correct. Okay. So the way in case of softmax, what we did was given any value, we converted that into 0 to 1. Correct. Here in case of sigmoid, any value was converted by sigmoid function into between 0 to 1. Here the softmax function is also between 0 to 1. Okay, between 0 to 1, and this is how it computes that. All right, any other questions? Balaji, Bintao, Gigi, Kamal, Noor, Pavan, Pratik, and Saruk, and Abhinav. All right, should we move ahead? A question from Binta is that what does it mean by dot revel? Dot revel basically converts, I think it converts the two-dimensional array into single-dimensional array, right? Let me just show you. So let me just see where, this is where we are using, right? So let's take a case of y revel and normal y, okay? So we have y and, okay, let's take a look. So here we have y, okay? All of these, okay, is a single array. And then, okay, let me just see. Let's say if we have y equals np dot array and 1, 2, 3, print y and print the, okay, just a second. And where did it go? Okay, let me take a better example. So we have, say, x1, right? X1 is two-dimensional array, and we say, what is that? Shape of x1. Sorry, x1 dot shape. Okay, and we say x1 dot, not x1, we'll say x1 dot revel. Okay, so you can see that it's the shape. I think this is better. Just take a look. You can see x1 is two-dimensional and x1 dot revel is one-dimensional. So it converts it converts the two-dimensional array into one-dimensional. That's what we were discussing. Thank you, Balaji. Yeah. So if something is one-dimensional, it will just return one-dimensional array. Thank you. Make sense, Binta? Okay, great, great. Yes, softmax is not one versus all. Softmax is basically the computing style is different. Okay. So essentially at every point of time, this kind of cost function is going to be there, and rest of the theta computation will also change. A question from Noor: can you explain decision boundary further? What parameters can affect the decision boundary and so on? Good question. Good question, Noor. So actually the SVM is all about decision boundary. I would like to describe decision boundary there. This is continued to SVM. We're going to solve the same problem using the SVM and would try to understand the various hyperparameters related to decision boundary and others. Okay. A question from Kamal is there a way to visualize the confusion matrix for softmax function? Yes, yes. So, okay. So question is, can we visualize the confusion matrix for softmax? Okay. So definitely. Let me just think. So the confusion matrix was essentially comparison between what is predicted and what is actual with respect to the classification, right? So, okay. So basically here, okay. So the confusion matter. So let me just think. So here, once you are doing the classification, even using softmax, the confusion matrix and other parts would remain the same. Why? Because the outcome of softmax is going to be that same way. So the all validations, all the testing will remain the same way. Okay, you're just using a different model to solve the classification problem, multi-class classification problem. Did I understand your question correctly? So I think you can actually use the same mechanism that we used earlier, even when we are doing the computation using softmax. Yes. Okay. Yes, that's the same way we could also do in this case. You're right. All right. All right. So here, okay. So this is where we are using confusion matrix, right? We could just import this part. Okay. All right. Now here the question is, let me see if I could do that. And oh, we haven't broken down this into the training and predict. Yes, that's one of the reasons. So let's say this is what we want to do, and okay, and also it is going to give us the confusion matrix here. So okay, so y predict equals, let's see, can I just do this? Can see that? Okay, so yes, this is that confusion matrix you could try. All right, so on x-axis it'll be the predicted, on y-axis it'll be the actual. That's how it is, right? Or the other way around. And then, yeah, okay. I'll take a look into this. If you could just add that to the notebook, it'll be great. Okay, let me just keep your question. I'll just put it in the notebook. Okay. All right. Great. Great. I think this needs to be more detailed, and that will make more sense. Great. Wonderful questions. Should we move ahead? All of you? Great. Great. All right. So let's move ahead. We are going at. Yes. Question from Noor is, earlier we only had one class. So we had only Boolean values. That's right. That's right. And so no, actually in the confusion matrix, in confusion matrix, we always had not Boolean values. I think we always had this the multiple numbers actually in the grid. In the grid. So we had this true, false, false, negative, false, positive, right, and so on, right? True, negative, true, positive, and false, negative, false, positive. How many of instances are in each of the buckets? So that's why. Just that in case of a binary classification, we have only 4 values. And in case of, say, we have 3 classes, we would have, say, 9 values, and so on. Okay, in the confusion matrix. So confusion matrix contains basically prediction versus this, and how many are in each bucket. All right. Let me just try to do this. Where did I keep it? And before that, you need to put this. Okay, great. Great set of questions. And okay. So in case of 2 by 2, 1, in case of binary classification, I think this is true positive. Okay. And on the y-axis, it is that, let me just go back. Where did we draw that? Yeah, let me just show you. So remember that this was like this. Yeah, this is a better representative. So here on the y-axis is the prediction. This is something which we need to remember. On y-axis is the prediction. On x-axis, it is the actual, right? On x-axis, it is the actual. So here wherever we are doing it. So if you see, we are saying that the the actual 1, 0, 1, 2. Okay, so 50 of them are actually predicted correctly. Okay, and 47 of 0 were predicted as 1 as well, while the only 3 were predicted as 2 out of 2. Okay, and so on. So there must be some other problem with our data set. Okay, that will be some. Okay, so actually y is only 0 and 1s, and y predicted is 0, 1, and 2. That's the reason. Okay, so that's one of the reasons why we are getting such awkward results, and therefore, yeah. Okay, so let me just try to predict y. Okay, y predicted is this, and y actual is correct. Now let me just show you the confusion matrix. Now you can see this is better. Okay, so after this, if we run, let me put all the code together in a nice fancy way. Okay, although it's not a right way to do it because we are just doing the predictions on the training data set. Now it looks better, right? So we are saying that 47 of what 2 are predicted as 2, while 3, okay, the Virginica is being 3 of the instances of Virginica are being predicted as the verticolor, right? So 3 like this. So rest of it looks good. That's correct. So yes, in very simple words, what Kamal is saying is correct. So the model is very confidently able to identify setosa, but is getting confused slightly between it's like 6% confusion uh, in the versicolor and virginica. Okay, good, great question. Can we print them in percentages? I think you can just do the multiplication and then you can do the percentage. And how do we, yeah, question would be how do we do the percentages? Maybe we can just divide by total number of instances of each, and that's it. All right, great questions. Keep the questions coming. That's the way we all learn. All right, wonderful, wonderful. So what all have we learned so far? What we have learned so far is we learned about linear models. We learned about before that we learned about the classification, and before that we went through the end-to-end project, and before that we went through the overview of machine learning, and before that we went through the Python course and NumPy course. All right, so we are doing good so far, and I'm seeing that the team is also pretty active and is doing good. So team as in the class. Okay. So now let's try to understand something different. Just like linear models were one technique to solve various problems. So with the linear training models, we even use to solve the higher degree of problems, like using the polynomial, uh, what do you say, polynomial degrees, and we were able to solve really complex problems, right? Using linear regressions, we were also able to solve the what do you call the classification problems as well as multi-class problems. Okay. All right. Let me also share this with all of you. That's okay. And so let me just change it to anyone. Okay. Please don't share the slides. They are a little confidential. Okay. Ajin, don't share with anybody outside the class. So, yeah. Wonderful. Wonderful to have all of you in this session. Let's move ahead. So support vector machines is another technique similar to the linear models. Okay, so we will see and understand the SVM. Okay, but we won't be going into the derivations, as in derivation of formulas and exact technique of SVM. And because that could be a little just too much of maths. If you guys want, I can hold a separate session outside the class, but keeping in the session would be really hard. And let me see if it goes well, then we can plan. Okay, the derivations of the formulas could take a lot of more time. And if you guys want it, then I can go ahead. All right. So great. So support vector machine is basically the another technique to solve various problems, specifically the classification ones. So you remember the general flow of machine learning. We take the data set, divide the data set into training samples, and we train the model using training data set. Okay, there can be several models depending upon the problem statement, and one such model is SVM. So support vector machine is, and the way we used the linear regression to solve classification as well as regression problems, similarly, we could use the support vector machines for both. Okay, so support vector machines is a very powerful and versatile model. It's capable of performing linear and non-linear classification. Okay, as well as regression, as well as outlier detection. So it is suitable. It is actually a pretty good solution to for classification, regression, and outlier detection. Okay, so it's well suited for small and medium-sized data sets. So the third technique would come as decision trees. After SVM, we'll talk about decision trees. So the first technique to solve problems were linear regression, then SVM, then decision trees that we will talk about. And afterwards, we will solve the similar problems using the deep learning, the neural networks. Okay, so essentially, we are trying to solve and improve the effectiveness of our model by using various kinds of algorithms. So one of them is SVM. So in this session, we will learn about linear SVM classification, then nonlinear SVM classification, and SVM regression. In the previous session, you saw that we were able to distinguish or separate one flower from another, right? Because the separation was linear, the line was linear. If that's not a straight line, then the usual regression systems cannot help there. But SVM does does can solve the nonlinear regression. Okay, so linear SVM classification is basically, let's just start with the SVM classification, and then we'll talk about regression later. So the linear SVM classification, or we call it SVC, is basically a supervised learning problem whereby we have specifically the classification. The objective classification is to identify something, like the one which we did earlier was to identify a digit from one another, or using the multi-class one. Either binary or multi-class. The other example could be identifying the spam. Okay, a quick question to all. What type of classification is this? Is it multi-class or binary? Quickly. Correct. Correct. It's a binary classification. Okay, and now the flower ones, was it binary or multi-class? That's right. It was multi-class classification. And okay, similarly, the credit card fraud is also classifying a credit card transaction as fraudulent or not is binary, correct. And this one, the face recognition. Which multiple? Is it multi-class or multi-label? So in a photo, there are 3 persons. So or there could be multiple things. So yes, it is a multi-label classification. All right. So while doing this classification earlier, which classifier did we use? Anybody? And you know, right now, what is SGD? SGD? So SGD classifier, not SDG. SGD classifier is stochastic gradient descent classifier. Okay, very good. Now, and here we did the binary classification, right? Now, a question to all of you is, what is the classifier that we use for multi-class? Anybody remember? Which classifier did we use for multi-class? That's right, we used the OVA, but we also showed you an example of OVO. But SGD classifier was internally using OVA. All right, great, great. Now let's try to understand what it means by linear classification. Okay, from here we will continue tomorrow. So great. All right. Thank you, everyone. We will start from here. This is where the SVM starts, actually. So we'll start from the linear classification tomorrow. All right. Thank you, Abhinav. Thank you, Balaji. Thank you, Bintao. Thank you, Gigi. Thank you, Kamal. Thank you, Noor. Thank you, Pavan. Thank you, Pratik. And thank you, Saruk. I look forward to see you tomorrow again at the same time. Okay. Okay. Thank you, Noor, for letting me know that. I will just take a look at it. Okay. Thank you, everyone. I look forward to see you next week. Not next week, tomorrow. Bye-bye. Have a good day. All right. So Kamal is saying that his son is also attending the class, and he said, "Type thank you so much for the class." I see. I see. All right. So say thank you to from my side also. Bye bye. Have a good day.